We're very excited to share our work on GO-LoW, the Great Observatory for Long Wavelengths. So, what is GO-LoW? GO-LoW is a new kind of space telescope, a mega-constellation telescope. Very long radio waves, longer than about 15 meters, cannot get through the upper part of the Earth's atmosphere, the ionosphere, so we can't observe them from Earth's surface. Long wavelengths require a very big telescope to observe them, hundreds to thousands of kilometers across for good resolution. GO-LoW uses many individual receivers working together wirelessly across a large area to form a constellation telescope that will allow us to finally see the universe in long radio wavelengths, something that has never been possible before. Why does GO-LoW matter? With this telescope, we'll not only get brand new maps of our galaxy, we'll also learn about magnetic fields of exoplanets, how the early universe evolved from the Big Bang to the stars and galaxies we see today, and much more. The technology we'll develop for this mega-constellation telescope will be broadly applicable to other scientific and commercial purposes as well, enabling even more innovation in space.
When we look up at the night sky, we can't see them, but everywhere there are exoplanets singing their aurorae into space. If we could see these radio waves, it would look like they're blinking off and on, like distant lighthouses. These radio aurorae carry important information about their planets. They can tell us whether or not a planet has a magnetic field, how strong it is, how fast the planet is rotating, and even hint about the dynamics and material properties inside of each planet. Studying exoplanet radio aurorae and the magnetic fields that they trace is a key science goal for GO-LoW. Planetary magnetic fields are an important piece of the habitability puzzle, and we need to learn about them to better understand our neighboring worlds. Interferometry is a technique that allows many separate antennas to work together. Through phase measurement, the antennas form a virtual telescope with an effective diameter that is equal to the largest distance between antennas. This is the technique that was used to make an image of a black hole, and more recently, the image of the first known extrasolar radiation belt. GO-LoW is a constellation telescope. It's made up of many thousands of free-flying spacecraft, each with its own radio antenna. These spacecraft can be rearranged into many different configurations to support different science cases. For example, regular spacing and relatively short baselines are good for cosmology experiments, while longer baselines and a wider range of spacings are good for imaging the galaxy. GO-LoW's reconfigurability and flexibility also mean that it can start doing science with just a fraction of its total antennas, and its capabilities will grow as more are added. Spacecraft that fail can also be replaced, either by others already in the constellation or with a new shipment from Earth.
We studied several constellation architectures for GO-LoW to determine the best balance between engineering complexity and achieving science goals. We selected a hierarchical architecture with many small listener nodes that collect data and a smaller number of larger and more capable communication and computation nodes. This architecture allows us to pack up to 13,000 listener nodes into each launch to make the overall constellation very sensitive, and it also allows us to leverage the processing power and high data rate communication provided by the CCNs. The listener nodes are equipped with vector sensor antennas, which collect radio data at a rate of about 2 gigabits per second. The full constellation collects upwards of 30 terabytes per second of raw data when observing. The listener nodes transmit their data over a short-range radio link to their local CCN. The CCN processes the data to reduce its size by at least a factor of 1,000. Before using a laser communication system, to transmit the data back to Earth. We're still working to find the optimal ratio, but we expect to have between 100 and 1,000 listener nodes for every CCN. To turn each listener is relative to every other. One of the big innovations of GO-LoW will be deploying a large wireless network in space to facilitate data transfer and localization of each listener and CCN node. We'll use a cooperative localization protocol along with high CCNs and periodic updates from Earth to regularly map out the constellation. Because GO-LoW observes the universe at long wavelengths, the precision with which the position of the nodes must be measured is about a meter, which is achievable with standard ranging techniques. Demonstrating interferometry at long wavelengths can be a stepping stone to interferometry at shorter wavelengths, where the precision requirements are more challenging.
The listener nodes will be small and simple so that we can fit a large number into each. Throughout this study, we're exploring different form factors and their potential launch vehicle packing densities. A 3U CubeSat, which is approximately the size of half a shoebox, is a leading contender, with enough room for all critical subsystems and enabling thousands of nodes per launch. Listeners will have a deployable science antenna, a high-sensitivity radio, and an RF communication system to talk within the constellation, including to the larger communication and computation nodes. They will also each have a small propulsion system for attitude corrections and constellation maintenance maneuvers. The science antenna will deploy from the listener node to a full size of several square meters. The vector sensor antenna, which is composed of 3 dipole antennas and 3 loop antennas, is the leading contender because of its excellent polarization performance, good sensitivity, and all-sky viewing capability. The communication and computation nodes, or CCNs for short, will be bigger ESPA-class spacecraft, approximately the size of a mini-fridge, in other words. They will each have an optical communication system to talk to Earth and downlink science data, as well as some backup RF communications. They will also have substantial onboard memory and processing resources to handle the data coming in from the listener nodes. The GO-LoW concept takes advantage of next-generation launch vehicles with large diameter fairing, like SpaceX's Starship. Several launch vehicles filled with thousands of listener nodes, as well as some CCNs, will be launched to low Earth orbit. Once there, the launch vehicles will be refueled by previously launched propellant tankers, as in SpaceX's planned Mars mission architecture. Next, the launch vehicles journey to an Earth-Sun Lagrange point, like L4, and upon arrival, the nodes are deployed. Earth-Sun L4 forms an equilateral triangle with both the Earth and the Sun, and is a very gravitationally stable point in space, requiring minimal propellant once the constellation gets there. And the large distance from the Earth, 1 AU or 93 million miles, means less radio frequency interference, which can otherwise threaten to overwhelm GO-LoW's sensitive measurement.
The best map we currently have of the sky at wavelengths longer than 15 meters comes from the Radio Astronomy Explorer 2 spacecraft, launched in 1973. The RAE-2 map was an impressive technical achievement, but it has now been 50 years since we've had a new view of the low-frequency sky. GO-LoW will be able to map the low-frequency sky with higher resolution and full coverage, producing maps like this one from the Planck spacecraft, but at much longer wavelengths. This extraordinary map reveals not just the brightness distribution of the sky, but also the magnetic field threading our Milky Way galaxy. At longer wavelengths, we will see exoplanet aurorae in our local neighborhood blinking on and off against the backdrop of the never-before-seen low-frequency galaxy. GO-LoW will show us the sky in a new light, including the plasma that fills the space between stars. It will look back in time to the cosmic dark ages, and it will allow us to get to know our neighboring exoplanets much better by listening to their aurorae and measuring their magnetic fields. These magnetic fields are key to how planetary atmospheres evolve, which may determine whether or not life has a chance to develop. The GO-LoW team is grateful for the support of the NIAC program. Please stay tuned for our Phase 1 final report in the new year. Thank you very much.